Hello, welcome back. So in this video, we will run the analysis on the logistic regression. First of all, log into the Brightspace and then go to the R videos, sample R code. And there's a data set called the emission data set. So you want to download this emission data set. So let's click on it. It's in the CSV file, so download that. Okay, and let's go back to the RStudio. So before we go to RStudio, let's take a look at the data set really quickly. Let's open this data set. Okay, emission CSV. So this is the data set about a graduate emission data set. This data set, there are 4 variables. First one is emission. So we have 2 categories. Either 0 is not emitting, and 1 is successful emission. Right? So and then we have GRE score, GPA score, and a rank. And in this case, the rank about the institution varies from 1 to 4. And rank of 1 have the highest prestige, and with those with the rank of 4 have the lowest prestige. So that means rank 4 probably is something like a local community college, and rank 1 will be those highly selective private universities. So those kind of like the ideas how this rank works. Now let's open the RStudio. First thing, we will load a data set. So go to File, and then you're going to take a look at Import Data Set. For all the CSV file, you're going to go using this front text option here. And then let's load that data set into the RStudio. So you see this is going to be automatic importing, and keep the name as emission. Okay, then we can do import. Now the data set has been imported, and we're going to go to new file, and then we're going to open the R Markdown file. So we're going to code, we call this Logistic Regression. And then we're going to save it as a PDF file, and then click on OK. So now that's we get this. Now again, one more time, we're going to delete all these unnecessary lines. Let's start with the loading the. Okay, so let's start load the ggplot package. Right, so I'm gonna press this ggplot package. And let's get a coding block. And here we're going to do library part 2. And summary. We're going to take a look at summary of the emission data set. And also we're going to take a look at STR, string of our emission data set. And let's close the coding block. Let's run this code. As you can see, emit, first variable emit, emission status, it's either 0 or 1, right? 0 is not emitted, 1 is a successful emission. So, and then GRE score goes from 220 all the way to 800. 800 is a perfect score. So here, Q1 is 520, median is 580, mean is 587.7. Q3 is 660, and the maximum is 800. So some people score perfectly in the SGRE test. And then GPA go from 2.26 and all the way to 4.0. Right? And mean and median is somewhere around 3.39. And then rank, it's rank 1, 2, 3, 4, right? Rank 1 has the highest prestige, highest privilege. And then rank 4 has the lowest prestige. And then if you look at the data frame here, STR means we look at the data frame, emission is integer. Indeed, it's not integer, right? It's a categorical variable with the two layers. 0 not emitted, and then 1 is emitted. And GIE is definitely the numerical data integers, which is this is a good category here. Classification, right, of the, and also the GPA is numerical, which is also good. It's numerical data. But the rank is not integer, right? It's gonna be categorical with 4 layers. So later we're gonna change this rank or convert the rank as the categorical data. And here we try to come up with a model. It's called a logistic regression model, used to estimate the probability for each individual graduate applicant, right? And then see how the model plays out. So the logistic regression is highly useful to model the decision-making process in terms of like you apply for the credit card, right? Either approved or rejected, that sort of scenarios, or either apply for a car loan, student loan, or like a mortgage, all those high-stake financial decisions or like personal decisions. So this is very, very useful stuff. So the next thing, first of all, we're gonna. So from this above, we see that we need to convert. So let's convert it. So this is a very important step. Is converting the rank as categorical data. So again, we're going to code it block and emission $sign rank, and then turn into as a factor. So we do as factor emission. Factor meaning we are changing this rank variable as a categorical data with 4 layers. Emission $sign rank. And then let's look at a string str of the emission one more time. And as you can see, we should see a categorical factor. We'll take a look at this one more time. It should be, now this is a factor with 4 levels. Okay, so that's what we want. Factor means categorical variable with 4 levels. Level 1, 2, 3, 4. And then once we do this, then we can start running the. Let's take a look at the graph first, right? So let's use a ggplot to take a look at the relationship between the GPA and also the emission status. So now let's use the ggplot to visualize distribution of data values, predictor variable GPA. Let's see how strong is the relationship between the GPA and also the emission status. So let's get a coding block. And ggplot. Condition that x is GPA, y is the mid. And look at the GMG. GMG meaning we're going to get a scatter plot for these two variables. Height equal 0.05 and alpha equal 0.1. Okay, then let's run the code. So right here we get this graph, and let's analyze it really quickly. So as you can see, we get so 0 is not admitted to the graduate program, and then 1 is a successful admission to the graduate program. And as you can see, as the GPA increases, it looks like the rate of success rate increases. The most dense area is somewhere here, right? Somewhere between like 3.25 all the way to 3.5. This is very dense, not being admitted, right? And then as you can see, and when the GPA increases, that the admission rate increases, especially when it's at 4.0, the admission success rate reached the peak. So this is what we see. So basically, our conclusion here is, as the GPA increases, the probability of admission also increases accordingly. So that's the first thing. And then we're also going to take a look at the let's use the ggplot to visualize distribution of data values for predictor variable GIE score. So very similar code. I'm just going to copy this coding block to save some time. Now here, I'm just going to change it to GIE score. And then let's run this code. So we see a similar pattern as the GIE score increases from, let's say, 200 or 220 all the way to 800. And you see this become denser. The block become denser. So that means probability of success increases, right? Probability of admission increases. So basically, it shows a similar pattern as the GPA. So one more time, our conclusion is, note, as GIE increases, GIE score increases, the probability of admission also increases. So you have higher chance of being admitted to the graduate program when this GIE score gets better. So now one more time, I'm going to just copy everything here. So I'm going to use the ggplot to visualize distribution of data values for predictor variable of the rank. So it's rank 1, 2, 3, 4. So now here I'm just going to use rank. X variable is rank. Yeah, so let's run the code one more time and see what happens. So in this ggplot here, you see that as the rank increases, right, from rank 4 all the way to rank 1, the probability of emission also increases. So you get a lot higher success rate in rank 1. Rank 1 is kind of like around 50%, right? And then the other rank is all below 50%, especially rank 4. The success rate is very minimal, right? Maybe somewhere around maybe about 20%. So definitely rank 1 has a lot higher chance of being emitted. So as you so similar patterns here, right? As the note, as the rank of the institution increases, the probability of emission also increases. So that's basically what we see from the now next we're gonna create the logistic regression model to predict emission status with the GPA as the only predictor variable. Let's see how that goes. So one more time, we get a coding block, and then we just go call this model 1. And we use this code called generalized linear model. GLM represents generalized linear model. So emit, coding wave, GPA, and then data is emission data set, and a family is binomial. So logistic regression belongs to binomial family. And then we're going to get a summary of model 1. So let's run the code. It looks like so first of all we get this y-intercept, which is minus 4.3576, and GPA, the coefficient beta 1 is 1.0511. If we look at the z-score, is very large, right? Bigger than 3 standard deviation, and then above the mean, and then the p-value is extremely small. So as you can see, the GPA is very significant predictor here. So some of the so if you want to write this logistic regression model, I'm just going to express this. So this model will look like this. Note here the logistic regression model. It's going to be ln of p over 1 minus p. P is probability of success, and then 1 minus p is probability of failure. That means probability of success, it's called odds ratio. Probability of successful emission over probability of failure, probability of not being emitted. And this is going to be equal to beta 0 plus beta 1 times x variable x. Here we only use one predictor variable, and then if you want to put in a concrete term, we ln of p over 1 minus p, and this is equal to minus. So we take the slope coefficient and also the y-intercept. So y-intercept is minus 4.3576. And then plus 1.0511 times GPA. And then from here, we can actually solve for P. And then we use this to make a prediction. Right? So if you want to solve for P, so P is going to be equal to ln of exp, right? Exp of minus 4.3576, meaning e raised to that power plus 1.0511 times GPA over 1 plus exp. Let me just copy this. So, for example, if you know the GPA of any student, target GPA as, for example, let's say with a 3, here we can calculate probability for that for the student with a GPA of 3.0. This is how we basically utilize this logistic regression model to make prediction. Now let's just get a coding block and let's use this model to make prediction for this entire 400 applicants. So we will predict. So before that, make prediction using the above logistic regression model. And from there we get a coding block, and then we call this PROB1, right? Probabilities. And we do the predict model 1 according to model 1. Type is response. And we take a look at all these probabilities, and we're going to run the result to 3 decimal places, PLB1 to 3 decimal place. There's 3 here indicating 3 decimal place, and n equal to 400. 400 applicants here in the data set. And let's run the code. And as you can see, we get all these 400 predictions with the corresponding probability values. And we can go back matching each candidate, right? Like with a GPA, this first candidate is GPA 3.61, and looks like it's not admitted. So if you go back here, it looks like probability of admission is only 36.3% the chance. So basically, we can match in each candidate with the corresponding probability values here. And if you scan through, we're going to see the lowest probability and the highest probability. I do see something like 0.462. It's candidate number 396. This one has pretty high chance of being admitted. And if you go down there, you know, we can look at that 396. Right, look like, yes, look at 4.0 GPA, perfect GPA. That's why the probability of success, probability of admission is highest among all the candidates. So that's basically, we can utilize this, you know, to get an overall picture in terms of using. And then now let's use this code and make prediction using. Okay, now let's run the logistic regression model using the GRE as the only predictor variable. So create a logistic regression model, copy all of this. Okay, paste down here. Now next thing, let's create a logistic regression model to predict admission status with the GRE as the only predictor variable. Now here, I'm going to change this to GRE. Then I'm going to call this model 2. And this is going to be called the summary of the model 2. And let's see what happened here. And based on the outputs here, looks like GRE is also a highly significant predictor variable in this logistic regression model. And B0 is minus 2.901344. B1 is 0.003582. So basically, we can rewrite this logistic regression model as got to change the variable to GRE. And then the coefficient here, we can just copy this. B0 is this. Goes here. And then B1 is 0.003582. Goes here. All right. Now I just change a little bit to change this inside the parentheses with the corresponding result above. So that's basically how we end up with this probability of success, right? Probability of omission. Anytime we plug in GRE score, we're going to get unique probability values. So, and then we can make the prediction using the above logistic regression. So we're using this. So I'm going to call this PROB2, and then it's from model 2. And we're going to run it to 3 decimal place again, PROB2. So let's see how that goes. So let's run the code. And we get all the probability values using the above logistic regression model 2. I'm using the GRE as the sole predictor variable. So it looks like yeah, we have all these different probability values. And I see a high score here of candidate 399. It's 0.403, meaning with a 40.3% of chance being admitted to the graduate program. That's high. And then if you look at the first candidate, it's pretty low. It's 0.177. It's only 17.7% of chance. If you go back to the original data set, it looks like candidate 1, GRE only 380, right? So that's not good. And that is why, this probability value is so small. Now I'm gonna reuse this code. I'm gonna use the outputs. Now let's create a logistic regression model using the rank as the only predictor variable. So now it's a rank. Now we're gonna call this model 3. And then it's called model 3. Let's see how that looks like. And we'll look at the model 3, and it looks like rank 1 is the default factor, and for rank 2, rank 3, and rank 4, they all are significant predictors because of the p-value are all smaller than 0.05. Especially rank 3 and rank 4, it's highly significant. So, meaning has a strong correlation between the emission status and also rank 3, rank 4. It's slightly higher compared to rank 2. So that's our logistic regression model using the rank. And if here, then if you want to write a model, it's going to be, it will be written like this. So we take this intercept first, it goes here. So the slope coefficient for rank 2 is this. And this is basically rank 2 and plus minus and minus. Just become minus. And again, this is plus minus is minus. and times rank 3 plus this coefficient times rank 4. So that's our logistic regression model. And then basically, if let's say it's in a rank 2, so rank 2 becomes 1, the rest of them become 0. And we can use that to make prediction for the probability of successful emission. So right here, if you want to solve for P, it looks like this. This thing becomes this. And yeah, so probability value comes from this. And then now let's use this model to make prediction about probability of successful emission. So we call this PLV3. Predict using model 3. And then we're going to run this PLV3 to 3 decimal place and we got 400. And let's run the code. And if you look at the results, here the candidate number 3 has a 54.1% chance being emitted. I suspect this will be in the rank 1. Right? Go back, let's take a look at it. Yeah, you see candidate number 3 and 4 both in the rank 1. No, actually candidate 3 is in the rank 1, right? Harvard University is, and it's the highest rank. And candidate number 7, same thing, right? It's in rank 1. It's being emitted. So successful emission. So go back here with the highest probability, and then 7 with the highest probability. So that also boosts as the rank improves, and then the probability of success also increases. Now let's create ggplot, a little bit more sophisticated ggplot. Create more sophisticated ggplot to take a look at each predictor. Take a look at each predictor variable. Just get an overall picture one more time. So get a coding block, curly wave, and let's do ggplot one more time. Emission dataset, that X is GPA first, Y is emit, and next thing G on jitter, and using the same height. Height is 0.05. It's basically the bubble on the graph. We want to separate it, using this height measurement. So alpha remains the same 0.1, and G on smooth. I'm going to smooth this, make a smooth curve. Method, we're going to call this generalized linear model, and then we put into method argument list binomial, and SE equals false. Let's close the coding block, see how that goes. And as you can see, you see that as the GPA increases, this is showing the overall trend, and the probability of success increases, right? It's going from about 12.5% all the way up to 47%, somewhere close to that, right? As GPA increases, you see the overall trend. Now let's look at the second predictor variable, I'm going to reuse this code. Right, let's change the GIE to GPA. Yeah, GPA to GIE. Okay. Let's see how that goes. I'm using the same code, and then we're going to look at it one more time. Now, based on this graph, again, as the GIE score increases, the admission rate is going from about 12% all the way up to about 50%. And that matches with what we see from the prediction, about prediction. So this curve here indicates the probability at each point, right? Each GIE score in this case. Now let's look at the rank one more time. I'm going to reuse this code. Let's copy this and then change this X to rank. Let's see how that goes. And since rank is a factor variable, so it doesn't show the overall. Basically, just rank 1, 2, 3, 4. So it's not a continuous random variable. That's why we don't see our prediction. But if you look at the density level for 1 and the density level for 0, you definitely see that rank 1 has the best chance of being admitted to this graduate program. Rank 4 has the lowest chance. It's just very few people get admitted compared to a lot of people get rejected. So that's what we see from this graph. Let's create a logistic regression model using all predictor variables, right? Let's generate the logistic regression model using all predictor variables. So let's get a coding block, and we call this model flow. And we use the generalized linear model, mid, curly wave, and a dot. That means we're using all predictor variables, comma, delta is admission, and a family is binomial. And then we're going to take a look at summary of the model flow. It's the full model, basically. See how that goes. And when we examine the outputs here, looks like all of these are significant predictor variables like GIE, GPA as 1 star. They are significant predictors. But compared to rank, I think rank probably is a better predictor variable compared to the other two, especially rank 3 and rank 4 has 3 stars, right? So that's a very significant predictor variables in this case. So for the overview is all these predictor variables are good. And then again, we can use this to make prediction, right? We're going to call this, I'm going to just clear out the outputs. Now, let's make prediction using the model flow. And one more time, we're going to get this. We're going to call this PLB4. We do predict using model flow. And then type this response. And then we're also going to run it. Run PR will be 4, 3 decimal place. N is 400. We have 400 candidates here. See the outputs very quickly. And when you look at outputs, look like candidate 3 has very high chance of being admitted. To go back to candidate 3 has GI score of 800, GPA of 4, and from the top tier private universities. So that's why this person has a 73.8% of chance being admitted. Look at candidate number 1, the chance of admission very low, it's 17.3%. Look into that, it's GIE 380, GPA 3.63, and it's in a rank 3 institution. So this is so that's why the chance is so low for this candidate number 1. All right. So and then if let's say we're gonna use this to make prediction, that's just hypothetically speaking, right? If you want to make prediction for any candidates, right? So predict probability of admission with GPA of 3.44, GRE of 633, and a rank of 2. And this is how we do it. Again, get a coding block, coding wave, and then we do test. But we'll call this test 4 from the model 4. Putting this data frame, GPA of 3.44, GRE of 633, and rank of 2. And now we do predict using model 4. Type response, and then from the test form, using the test form. And let's just close the coding block. Let's see how that goes. Let's run the code. And it looks like the probability value is 38.55% of chance of being admitted. And if you're checking all 4 models, right? We can check all 4 models. Compare all 4 models using the AIC or BIC values. So let's just quickly do R. And then here we do AIC, model 1, model 2, model 3, and model 4. And similarly, we do BIC. Let's see, let's take a look at the outputs. Let's run the code. If you look at the BIC, you see model 4 has the smallest BIC. And with the AIC, same thing, right? Model 4 has the smallest BIC values. So model 4 is the best. So the full model is the best in this case. According to AIC and BIC values, model 4 is the best model. Because it loses the least amount of information. So this is what we see. The model 4 is the best. Now, next thing we're gonna install a couple package and then go through the model selection process, just like a multiple linear regression. All right, so let's run. Some model selection, mechanics. Let's get a coding block. And then we're going to need the library math package. Okay, and we're going to create this table, create a table to summarize our submission and $submit. Let's close the block. The overall picture is that out of 400 candidates, 127 are being admitted and 273 are rejected. So that's what we see. So again, it's about 1 to 2 ratio, right? So 30% of people being admitted, and maybe 40% of people being 40 or 30% of people being admitted, and then the other 70 being rejected. That's a breakdown. And then now that's in order to get a model selection process going, we need a full model. So create a full model with all predictor variables, and have coding block, coding wave path, and then we just call this full model generalized linear model, admit using all predictor variables, GPA plus VIE plus rank. Data is admission. And then family is binary. And let's close the block. Yep, so we get a full model, and then also get a null model. Meaning null model is a model with a 0 predictor variables. So create the null model. Now using the above code, and then here just putting one here. Okay, that will do it. And a family equal to binomial, so make sure put binomial in a quotation mark. Look at that. So the null model has been, no, it's called a null model. Null model is created. And we're going to use this model selection, create a model selection from both directions. And we're going to call this a model. And it's using this AIC criteria to select the model. Now we start with the full model. And then direction is both directions. And then let's take a look at summary of STEM model. Let's see how that goes. It looks like if you look at the outputs, it failed to generate meaningful results, right? We can also copy this block, and then we start with the null model, see how that goes. Did that generate any meaningful outputs? So we start with the null model using the sequential selection mechanics, and it generates the same outputs, right? It failed to render a valid logistic regression model here. So then we can use the other two in the forward direction. So we just create a model selection process from using from the forward direction or backward direction. Forward. And for the forward, I'm going to call this forward model. Again, we use this AIC criteria. So AIC, we're going from the forward model. We always start with the null model and direction is forward because it's forward. So we start with a 0 predictor variable in our model. Let's get summary of forward model. See how that goes. Forget to get a coding block. And let's close the coding block. And let's run the code. And again, it looks like this forward model couldn't generate a meaningful output. Again, it stops at the null model. Now let's try one last thing, right, which is the backward direction. See if that generates. So create a model selection from the backward. So we're going to change this to backward. And then for the backward, we start with the full model. Direction is backward. Summary backward model. And let's see how that goes. If it generates any meaningful output. Just one quick thing. Going back to the earlier code, under this, when we generate the full model here, we need to get a summary of the full model, right? So here, insert this command here, summary full model. So we get this full model expanded. And also for null model, we also want to get a summary of null model. And then once we expand this, and we see the null model being fully executed. Now, if we create a model selection from both directions, now it does generate the meaningful outputs, right? Here it says, give us the overall model is going to be using a step model. It's basically GPA plus GRE plus rank. And then that means if you get a summary of the model, step model, you see all these predictor variables be there. Right, this one does generate the meaningful outputs. So I'm going to delete this and then go back. Full model. Again, summary full model. This one, yeah, this one fails to render a good meaningful outputs. But now if we do the backward, now again, if we generate the backward model here, it also gives us the full model as the best overall model. So as you can see, admission should be based on all three GPA, GRE, and then rank. So that's all three predictor variables should be there. And it does. So basically, what it's saying is, so our conclusion is basically both step model and then backward model give us the outputs. So note both step model and then backward model render yield the same best overall model, which is a mix based on all three predictor variable GRE plus GPA clustering. So that's our, we get confirmation from both model selection mechanics. Now, last thing, we're going to take a look at the confusion matrix. Go back to the model. And then we're going to get a coding block. And then PROBS. And I have to predict STEM model, using STEM model type response. And this model selection mechanics works well when we have a lot of predictor variables. In this case, we have 3 of them. So it's effective, but it's even more useful when we have let's say 10-20 predictor variables. That will make a big difference. Response. Let's finish this and predict. We're using if-else command. If the probability value is greater than 0.5, that means you have better chance being admitted. About 50%, meaning higher admission rate. And then otherwise, if it's below 0.5, it will be 0, meaning not admitted. And then let's create a table to summarize. We call it predicted equal to and actual equal admission $sign. So basically, this is where the confusion matrix kicks in. Let's see how that goes. Let's run the code one more time. And if you look at the confusion matrix, this 254 candidates here, we predict not admitted, and in reality is not admitted, right? So that's a true statement here. This is good, right? So this is called a true negative. And if you look at this, the second one, 97, the prediction is not admitted, but in reality, those 97 people are admitted. So this is an error, a mistake, right? This is the prediction mistake here. And then if you look at these 19 people, we predict those 19 people being admitted, but in reality, it's rejected. So again, this is a mistake. And then the last item here is we predict 30 candidates being admitted, and in reality, all those 30 people are admitted. So these two are 97, 19, those are the prediction errors. And again, it's called a false negative or false positive. We have true positive. This 30 is true positive. And then this 254 is true negative. And this 97 are false negative. And this 19 are false positive. Right? That's basically the layout of this confusion matrix. I'm going to save it really quickly as a PDF file. Right, on the downloads. And it's called a logistic regression. Save. I'm going to need it to. I'm going to need it as a Word document. Right? You can also need it as a PDF or like HTML. If you need it as HTML, that's pretty good. That's the end of the video.